Imagine staring up at the night sky, gazing at the countless stars twinkling against the endless darkness. It's a sight that's captivated humanity for millennia, each tiny point of light representing a sun, a world, a story waiting to be told. But what if I told you there's something else lurking in those shadows, something far stranger and more mysterious than anything you've ever seen? Hidden among the stars are cosmic enigmas, so bizarre they defy everything we thought we knew about the universe. And today, we're diving into one of the most mind-bending of them all, the elusive, almost mythical dark stars. These aren't just ordinary stars gone dim. Dark stars are something entirely different, theoretical giants that could rewrite the rules of astrophysics. Picture a celestial object so massive, so dense, that it doesn't shine like the stars we know. Instead, it lurks in the void, invisible to the naked eye, detectable only by the way it warps space itself. Some scientists believe these dark stars could be the missing link in our understanding of the early universe, remnants of a time when the cosmos was young and wild, governed by forces we're only beginning to comprehend. What makes dark stars so fascinating isn't just their strangeness, it's the questions they force us to ask. How do they form? Could they still exist today, hidden in plain sight? And if we found one, what secrets would it reveal about the nature of dark matter, black holes, or even the birth of galaxies? This is a journey into the unknown, where the laws of physics twist into something unfamiliar, where the universe holds onto its deepest mysteries with a tantalizing grip. So buckle up, because we're about to explore the shadowy edges of space, where the ordinary ends and the extraordinary begins. To understand primordial dark stars, we have to travel back in time, way back to the universe's infancy, just a few 100 million years after the Big Bang. This was an era before galaxies, before even the first ordinary stars had fully lit up the cosmos. Space was a swirling sea of hydrogen, helium, and something far more enigmatic: dark matter. And here's where things get wild. Scientists theorize that in this ancient cosmic soup, dark matter wasn't just floating passively. It might have clumped together in such dense pockets that it triggered a bizarre and powerful phenomenon: annihilation. Picture this: dark matter particles colliding and exploding in bursts of energy so intense they could have fueled the birth of stars unlike anything we see today. These wouldn't be fiery balls of hydrogen fusion like our sun. Instead, they'd be something darker, stranger, glowing faintly, not from nuclear reactions but from the sheer heat of dark matter self-destructing. Imagine a star so large it could swallow our entire solar system, yet so dim it would barely cast a shadow. That's the scale we're talking about: colossal, ghostly behemoths stretching hundreds of times wider than the sun, yet emitting only a fraction of the light. But why haven't we found them yet? Well, think of it like searching for a single whisper in a hurricane. The early universe was chaotic, and these dark stars, if they existed, would have been smothered in the swirling gases of a young cosmos. Even if they survived, their light would be drowned out by the glare of modern galaxies. And here's the kicker: they might not even be made of the same stuff as normal stars. Without heavy elements, they'd be almost invisible to our telescopes, detectable only by their gravitational fingerprints or the faintest infrared glow. Some researchers believe these primordial dark stars could have been the seeds for supermassive black holes, collapsing under their own weight to form the monstrous giants we now find at the centers of galaxies. Others think they might still linger in the deepest voids of space, relics of a time when the universe was a very different place. Either way, discovering one would rewrite the story of how everything we know, galaxies, stars, even life itself, came to be. The hunt for primordial dark stars is one of the most thrilling detective stories in modern astronomy, and the James Webb Space Telescope might just be our best lead yet. With its unprecedented infrared vision, JWST is peering deeper into the early universe than ever before. scanning for the faintest whispers of light that could betray the presence of these shadowy giants. But why is this search so crucial? Because finding even one dark star would force us to rethink the cosmic rulebook. Think of it like uncovering a fossil from a lost civilization. These stars aren't just oddities, they're potential time capsules, preserving clues about an era when dark matter shaped the universe in ways we can barely imagine. If they existed, their sheer size and unique energy source would have influenced how the first galaxies formed, how matter clumped together, even how the building blocks of life eventually spread. That's why astronomers are combing through JWST data with razor focus, looking for anomalies, objects too large and too dim to fit our current models of star formation. One tantalizing possibility: some of the bizarre blobs JWST has already spotted in the distant universe, glowing patches that don't quite match known galaxies or quasars, might actually be dark stars. These cosmic ghosts could be lurking in plain sight, masquerading as something else until closer inspection reveals their true nature. Imagine the implications. A dark star's composition, lifespan, and even its death throes would challenge our understanding of stellar physics. But the search isn't easy. Differentiating a dark star from a young galaxy or a black hole requires painstaking analysis of light spectra, gravitational effects, and temperature patterns. And even if we find a candidate, confirming it would demand entirely new observational techniques. Yet the payoff could be astronomical, proof that the early universe ran on rules we're only beginning to grasp. Every flicker of anomalous light, every gravitational wiggle in distant space brings us closer to rewriting cosmic history. The question isn't just, do dark stars exist? It's, what else don't we know? While primordial dark stars remain a ghostly possibility in the early universe, there's another cosmic mystery hiding much closer to home: objects born not from dark matter's eerie glow, but from the explosive death throes of massive stars. Picture this: a supernova, one of the most violent events in nature, but with a twist. Instead of collapsing into a neutron star or black hole, what if the star's core shattered into something even stranger, a dense, cryptic ball of quark matter? This is the heart of the quark-nova theory, and it could explain why some dark stars might be lurking right in our galactic backyard. Quark matter isn't your everyday ingredient. Under unimaginable pressures, the protons and neutrons inside a star's core could break apart into their fundamental building blocks, quarks, swimming in a searing, ultra-dense soup. If this happens during a supernova, the result wouldn't be a typical neutron star. Instead, it'd be something far more exotic: a quark star, an object so dense it defies conventional physics. And here's where things get eerie. Unlike neutron stars, which pulse with radiation, quark stars could be nearly invisible. Their surfaces might be so smooth and cold that they emit almost no light, making them perfect candidates for dark stars hiding in plain sight. But why would quark stars stay so stealthy? It all comes down to their structure. While neutron stars have rough, hot crusts that glow with X-rays and radio waves, quark stars could be wrapped in a bizarre quantum cloak, a layer of ultra-dense material that absorbs radiation instead of emitting it. Imagine a cosmic black hole impersonator, warping space with its gravity but without the event horizon. Some astronomers even speculate these objects could explain mysterious gamma-ray bursts or the odd gaps in pulsar surveys where stars seem to vanish without a trace. The hunt for quark-nova dark stars isn't just about filling a gap in our stellar zoology, it's about rewriting what we know about stellar death. If they exist, they'd challenge our understanding of matter itself, proving that under extreme conditions, the universe cooks up forms of material we've only theorized in labs. And the most tantalizing part, we might have already spotted them. Strange objects like X-ray dim neutron stars or certain magnetars with unexplained energy drops could be quark stars in disguise, their true nature masked by the very physics that makes them so alien. So the next time you look up at the night sky, remember, Some of those dark patches might not be empty space at all. They could be the graves of stars that died in ways we're only beginning to imagine, leaving behind remnants so strange they blur the line between science and science fiction. The universe, it seems, still has a few tricks up its sleeve. Quark matter isn't just a dense version of normal matter. It's a cosmic wildcard that forces us to rethink everything we know about how stars live and die. To grasp how bizarre this substance is, we have to shrink down to the quantum level where the usual rules of physics start to crumble. Inside an ordinary neutron star, matter is packed so tightly that electrons and protons merge into neutrons, creating a city-sized ball of nuclear paste. But quark matter, that's where even neutrons break apart, their components spilling out into a sea of free-flowing quarks, the universe's most fundamental building blocks. Under pressures 100 trillion times greater than Earth's atmosphere, quarks stop behaving like well-mannered particles. Instead of staying neatly bundled inside protons and neutrons, they begin to roam freely, forming what physicists call a quark-gluon plasma. This isn't just exotic. It's a state of matter so extreme it hasn't existed naturally since the first microseconds after the Big Bang. And if quark stars are real, they'd essentially be permanent snapshots of that primordial chaos, cosmic fossils floating in space with cores hotter than a supernova yet colder on their surfaces than a winter night. The implications are staggering. A quark star's surface wouldn't have mountains or cracks like a neutron star's. Instead, it could be a perfect, frictionless mirror, reflecting almost no light while its interior churns with quantum turbulence. Some models even suggest these objects might emit strangelets, hypothetical chunks of quark matter that, if they escaped, could convert ordinary matter into more quark matter on contact. It sounds like science fiction, but it's a real theoretical risk that makes quark stars both fascinating and slightly terrifying. Yet the biggest puzzle isn't their extreme physics, it's how they'd alter stellar life cycles. Normally, when a massive star dies, it leaves behind either a neutron star or a black hole. But if quark stars exist, there might be a middle path, a supernova so violent it shatters the neutron star it just birthed, triggering a second explosion, a quark-nova, that ejects jets of pure quark matter. Imagine the spectacle, a star dying twice, first in fire, then in a silent, invisible transformation. The hunt for these ghostly objects is already turning up clues. Some astronomers point to ultra-dense pulsars that suddenly go quiet, their radio beams vanishing as if something inside them fundamentally changed. Others study bizarre gamma-ray bursts with energy patterns that don't fit any known stellar behavior. Every anomaly could be a breadcrumb leading to the first confirmed quark star, a discovery that wouldn't just rewrite textbooks but force us to question what else might be hiding in the dark. Now let's venture into the quantum abyss where black holes might not be the dead ends we once thought. Imagine a black hole collapsing, not into an infinitely dense singularity, but bouncing back like a cosmic spring. This is the mind-bending idea behind Planck stars, a radical prediction from loop quantum gravity that turns our understanding of black holes inside out. Unlike the silent voids of traditional black holes, these theoretical objects could shimmer with quantum energy, briefly lighting up before vanishing into the dark. Loop quantum gravity suggests space isn't smooth and continuous but woven from tiny, indivisible threads like a fabric stitched together at the smallest scales. When a black hole collapses under its own gravity, this theory says it can't crush down to a true singularity. Instead, it hits a wall, a quantum rebound where gravity becomes repulsive, reversing the collapse. The result, a Planck star, a fiery core of trapped radiation glowing faintly at the heart of what we'd mistake for a black hole. Here's where the contrast gets stark. A traditional black hole singularity is a one-way street, a point of infinite density where physics breaks down. But a Planck star, it's more like a cosmic pressure cooker, holding the remnants of the collapsed star in a dense, hot ball no bigger than an atom, yet containing the mass of a sun. And because of quantum effects, this tiny powerhouse might emit radiation, glowing softly in X-rays or gamma rays before fading away. The implications are staggering. If Planck stars exist, they could solve some of black holes' biggest paradoxes, like the infamous information loss problem. Instead of data vanishing forever into a singularity, it might linger in the Planck star's quantum glow, waiting to be released. Even more tantalizing, some theories suggest these objects could explain fast radio bursts or other high-energy cosmic phenomena we've struggled to decode. Of course, catching one in the act would be like spotting a firefly in a hurricane. Planck stars would live for mere seconds before transitioning into a black hole's silent cloak. But that brief flicker of quantum light could rewrite our cosmic playbook, proving that even the universe's darkest corners still hold traces of brilliance. The hunt is on not just for black holes, but for what might be hiding inside them. The information paradox has haunted physicists for decades, a cosmic riddle wrapped in the very fabric of black holes. At its heart lies a brutal contradiction. If black holes swallow everything, even light, and slowly evaporate through Hawking radiation, what happens to all the information they consumed? According to quantum mechanics, information can't be destroyed, but black holes seem to erase it entirely. That's where Planck stars might step in, offering a breathtaking solution hidden in the quantum weave of spacetime. Picture a black hole not as a bottomless pit, but as a collapsing star that hits a quantum speed bump. In loop quantum gravity, space isn't infinitely divisible, it's made of tiny, discrete loops. When a black hole's collapse reaches the smallest possible scale, these loops resist further squeezing, creating a rebound effect. Suddenly, the dying star isn't vanishing into a singularity. It's bouncing back as a Planck star, a blazing core of trapped energy. And here's the key, that energy isn't just random noise, it's encoded with the original star's information, preserved in the quantum fireworks of the rebound. Now connect this to Hawking radiation. Traditional models suggest this radiation is thermal, carrying no information, like ashes after a fire. But if a Planck star flickers inside the black hole, even briefly, it could imprint that radiation with quantum fingerprints, a cosmic SOS broadcast as the black hole evaporates. Think of it like a message in a bottle, where the bottle is the Hawking radiation and the message is the scrambled but intact data from everything the black hole ever swallowed. The implications are profound. Instead of information vanishing into oblivion, it's temporarily locked in the Planck star's quantum structure, then slowly released as the black hole fades. This wouldn't just solve the paradox, it'd weave black holes back into the quantum universe's rules, proving that even the darkest objects play by the same physics as everything else. Critics argue we've never seen evidence of Planck stars, but supporters counter that their signatures might be hiding in plain sight. If a black hole's final moments include a Planck star's last stand, the burst of energy could mimic certain gamma-ray flashes or even explain why some black holes seem to evaporate faster than expected. It's a cosmic detective story where the clues are written in quantum code, waiting for the right telescope to crack them open. So next time you hear about Hawking radiation, remember, it might not be the end of the story. Behind the veil of a black hole's shadow, a Planck star could be whispering the universe's deepest secrets, proving that nothing, not even the void, can truly erase the past. The paradox isn't solved yet, but for the first time we might have a path forward, written in the language of quantum gravity. Picture a star not burning out, but frozen, caught in an endless pause at the edge of a black hole's abyss. This isn't science fiction, it's the bizarre reality of what astronomers call frozen stars, objects trapped in a cosmic limbo where gravity warps time itself. Near the event horizon of a black hole, the pull is so immense that time slows to a crawl. From our perspective, the star's light dims and reddens, stretched into invisibility by the sheer weight of spacetime. What was once a brilliant beacon becomes a shadow, a dark echo of its former self, suspended in a moment that never ends. To grasp how this works, imagine watching a clock fall toward a black hole. As it nears the event horizon, the hands would appear to tick slower and slower until they stop entirely. The clock hasn't stopped, time itself has stretched thin like taffy pulled to infinity. For the star, life goes on normally in its own frame of reference, but to us, its final moments are smeared across eternity, its light sapped of energy until it fades beyond detection. It's a cosmic illusion, a trick of relativity that turns a star into a dark specter haunting the edge of oblivion. The irony is haunting. A star that should be blindingly bright becomes invisible not because it's cold or dead, but because time has broken down around it. This isn't just theoretical. Astronomers have spotted hints of this phenomenon near supermassive black holes, where stars seem to vanish mid-orbit, their light redshifted into nothingness. Some even suspect these frozen stars could explain mysterious gaps in galactic cores, dark spots where stars appear to blink out of existence without a trace. But here's the twist. If you could somehow survive falling alongside one of these stars, you'd see it shining normally, untouched by the black hole's grip. The darkness is an illusion, a side effect of perspective. It's a reminder that the universe has a cruel sense of humor, hiding its most dazzling secrets in plain sight, just beyond the limits of our perception. So the next time you gaze at a black hole's shadow, remember, some of the stars aren't gone. They're just waiting, frozen in time, for an ending that will never come. Detecting frozen stars isn't just difficult, it's like trying to spot a shadow in a pitch-black room. The very forces that create these cosmic oddities also render them nearly invisible to our telescopes. When a star freezes at the edge of a black hole, its light doesn't just fade, it stretches into wavelengths beyond what our instruments can see, redshifted into oblivion by the extreme gravity. Imagine shouting into a windstorm. Your voice gets carried away before it can reach anyone. That's what happens to the light of a frozen star. Its photons stretch thinner and thinner until they dissolve into the background hum of the universe. Even worse, time dilation plays a cruel trick on observers. From our vantage point, the star's final moments are smeared across eternity, making it seem like it's hovering just outside the event horizon forever. In reality, it's already crossed the point of no return, we just can't see it happen. Current telescopes lack the sensitivity to pick up these ultra-faint, ultra-red signals buried in the glare of nearby stars and galactic dust. It's like searching for a single dying ember in a forest fire. But hope isn't lost. Next-generation instruments like the upcoming Nancy Grace Roman Space Telescope or the European Extremely Large Telescope could change the game. With unprecedented infrared capabilities, they might catch the telltale heat signature of a frozen star's last gasp, a faint thermal whisper lingering at the edge of a black hole's shadow. Other proposals involve networks of gravitational wave detectors tuned to the peculiar frequencies of stars tearing apart in slow motion, their space-time ripples encoded with clues about their frozen state. Perhaps the most tantalizing possibility lies in quantum optics. Some theorists suggest that entangled particles near frozen stars could exhibit bizarre behaviors, offering an indirect detection method. It's a long shot, but in astronomy, the wildest ideas often lead to breakthroughs. After all, black holes themselves were once considered mathematical curiosities until we found them. The universe has a habit of hiding its most profound secrets in plain sight, waiting for the right tools to reveal them. And when we finally peel back the veil, frozen stars might show us that the line between existence and oblivion is far blurrier than we ever imagined. Imagine a star that doesn't shine not because it's burned out, but because it runs on something far stranger than nuclear fusion. Dark matter stars are one of the most radical ideas in astrophysics, celestial objects fueled not by the fiery collisions of hydrogen atoms, but by the silent annihilation of dark matter itself. These wouldn't be stars as we know them, no blistering surfaces or dazzling light shows. Instead, they'd be cosmic ghosts radiating faint warmth while cloaked in near-total darkness. The theory goes like this. In the early universe, vast clouds of dark matter could have collapsed under their own gravity, pulling in surrounding gas until they reached stellar scales. But here's the twist. Unlike ordinary stars where fusion ignites in the core, dark matter stars would generate energy through particle collisions. When two dark matter particles meet, they might annihilate on contact, converting their mass into pure energy, a process eerily similar to how antimatter behaves. This energy would heat the star's interior, preventing total collapse, but with one crucial difference: the energy wouldn't escape as visible light. Instead, it'd seep out as low-frequency infrared radiation, invisible to human eyes. Structure-wise, these stars would defy every textbook diagram. Without fusion to balance gravity, they wouldn't need the searing temperatures of a sun-like star. Their cores could be relatively cool, with dark matter annihilation providing just enough heat to keep them puffed up. Some models suggest they'd be gigantic, hundreds of times wider than our sun, yet eerily dim, like smoldering embers in the cosmic dark. Their surfaces might not even have the turbulent plasma storms of normal stars. Instead, they'd be smooth, almost featureless, their outer layers too cool to emit much light beyond a faint infrared glow. The reason they'd stay so dark lies in their fuel. Dark matter doesn't interact with electromagnetic forces, meaning its annihilation wouldn't produce the photons that make stars visible. It's like comparing a bonfire to a radio transmitter. One blazes with light while the other hums with energy you can't see. If dark matter stars exist, they'd be the ultimate cosmic stealth objects, detectable only through their gravitational pull or the faintest heat signatures. What's wild is that some researchers think these stars might still linger in the modern universe, hidden in the emptiness between galaxies. Others argue they could have been the seeds for supermassive black holes, collapsing when their dark matter fuel ran out. Either way, finding one would force us to rewrite the rules of stellar evolution, proving the universe has more ways to build a star than we ever dreamed. The hunt is on not for light, but for the shadows cast by something far stranger. If dark stars exist, their influence wouldn't stop at the edges of these shadowy giants. They could sculpt the very architecture of galaxies. Picture a cosmic puppeteer, invisible but omnipresent, tugging at the strings of star formation and galactic evolution. Dark matter already makes up roughly 85% of the universe's mass, yet we've only seen its gravitational fingerprints. But if it can clump together tightly enough to ignite dark stars, its role becomes far more hands-on. These stars wouldn't just be oddities, they'd be gravitational anchors, warping the dance of gas and dust around them, seeding the birth of entire stellar systems in ways we're only beginning to grasp. Take the early universe, where dark matter's gravitational pull helped gas clouds collapse into the first ordinary stars. Now imagine dark stars acting as supercharged versions of this process. Their immense mass, radiating no visible light but bending space-time like cosmic boulders, would attract hydrogen and helium with terrifying efficiency. Gas streams might spiral toward them, compressing until they ignite into new stars, creating dense clusters where none should exist. Some models even suggest these dark stars could explain the puzzling brightness of certain ancient galaxies, their light boosted by hidden dark matter furnaces lurking in their cores, heating gas without the glare of fusion. But the real game-changer, dark stars could solve one of astrophysics' biggest head-scratchers: how supermassive black holes grew so quickly in the early cosmos. If a dark star collapses, it wouldn't leave behind the usual neutron star or black hole remnant. Instead, its sheer size, hundreds of times more massive than the Sun, means it could implode directly into a black hole with a hunger unmatched by ordinary stellar deaths. Overnight, a galaxy's heart could house a monster, feasting on surrounding matter and ballooning into the supermassive giants we see today. Yet the wildest possibility is that dark stars might still be hiding in modern galaxies, camouflaged among ordinary stars. Their gravity could explain mysterious orbital quirks in star clusters or the unexplained heating of gas clouds in deep space. Some astronomers even speculate they're the missing link behind dark matter halos, those vast, invisible cocoons enveloping galaxies. If dark stars formed in abundance long ago, their remnants could be the unseen scaffolding holding galaxies together, their gravity shaping spiral arms and stellar orbits without a single visible trace. The irony is delicious. The same substance that refuses to interact with light might have forged the brightest structures in the cosmos. And if we ever prove their existence, it won't just rewrite astronomy textbooks, it'll reveal a universe where darkness isn't the absence of light, but the architect of it. Electroweak stars sound like something ripped straight from a physicist's wildest dreams, and in a way they are. These aren't just stars with exotic fuel, they're celestial monsters where the very laws of particle physics twist into something unrecognizable. Picture the heart of a massive star collapsing, not into a neutron star or black hole, but into a searing crucible where temperatures reach 100 trillion degrees hot enough to blur the line between two fundamental forces of nature. At these unimaginable energies, the electromagnetic force and the weak nuclear force, normally separate, fuse into a single electroweak force. The result: a star that doesn't burn through fusion but through something far more extreme, the direct conversion of quarks into leptons, unleashing energy so intense it outshines entire galaxies for about 10 minutes. Let's break that down. In an ordinary star, fusion smashes hydrogen into helium, releasing energy as light. But in an electroweak star's core, conditions are so extreme that protons and neutrons melt into a soup of free quarks. These quarks, under insane pressure and heat, don't just collide, they transmute. Through electroweak burning, quarks transform into neutrinos and other particles, a process that releases energy 1,000,000 times more efficiently than fusion. It's like swapping a campfire for a nuclear explosion. The energy output is staggering. A single electroweak star could briefly radiate as much power as a supernova, all packed into an object no bigger than a city. But here's the catch. These stars are cosmic mayflies, here one moment and gone the next. That insane energy release isn't sustainable. Within minutes, the quark fuel depletes and the star's core collapses further, likely becoming a black hole. This fleeting existence makes electroweak stars nearly impossible to spot, but not quite. Some theorists suggest they might leave fingerprints in the form of ultra-high-energy neutrinos or gamma-ray bursts with bizarre spectral lines. Others speculate that certain unexplained supernova imposters, explosions too bright to be supernova but too short-lived to fit known models, could actually be electroweak stars flaring into oblivion. What's mind-bending is the sheer scale of forces at play. At energies this high, particles behave like waves, space-time itself warps unpredictably, and matter becomes a quantum froth where the usual rules don't apply. An electroweak star's core isn't just hot, it's a laboratory for unification physics, a place where the universe briefly reverts to a state unseen since the first trillionth of a second after the Big Bang. For those few minutes, such a star becomes the brightest, most extreme object in the cosmos, a fleeting beacon of what happens when nature pushes matter to its absolute limits. The irony: if these stars exist, they're both spectacular and invisible. Their energy might emerge as neutrinos, particles that streak through planets like ghosts, or as gravitational waves, ripples in space-time we've only just learned to detect. That's the paradox of the cosmos. The most violent events often leave the subtlest traces. Yet if we ever catch one, perhaps in data from neutrino observatories or next-gen gravitational wave detectors, it would be a smoking gun for physics beyond the standard model, proof that the universe still holds regimes of energy and matter we've barely begun to imagine. Until then, electroweak stars remain a tantalizing what-if. a reminder that even the most familiar objects in the sky might hide secrets more extraordinary than fiction. Proving electroweak stars exist isn't just about spotting them in the cosmos. It's about recreating the unimaginable conditions of their hearts inside supercomputers. Scientists are running simulations so complex they push the limits of modern physics, attempting to model what happens when a star's core crosses into a realm where the electromagnetic and weak forces merge into one. These aren't just equations on a chalkboard, they're digital crucibles forging virtual environments hotter than a million supernovas to see if nature could actually build such a star. Take the work being done at facilities like the Max Planck Institute or CERN theory groups. Their simulations start with a collapsing stellar core, its density skyrocketing as gravity overwhelms nuclear forces. But instead of stopping at neutron star matter, the code plunges deeper, tracking quarks as they're squeezed beyond recognition. At a certain threshold around 10,000 trillion degrees, something extraordinary happens. The quarks cease behaving like distinct particles and instead form a unified quantum soup, their interactions governed by the merged electroweak force. Energy output in these models spikes violently, not from fusion, but from quarks transmuting directly into neutrinos and photons, a process so efficient it could briefly outshine an entire galaxy. Yet the real challenge isn't simulating the ignition, it's proving stability. Electroweak burning is absurdly short-lived, and if the energy release shreds the star immediately, the phenomenon would be indistinguishable from a supernova. That's where recent breakthroughs in lattice quantum chromodynamics come in. By modeling quark interactions at femtosecond scales, researchers have found hints that magnetic fields in the core might temporarily bottle up the energy, allowing the star to burn steadily for those critical few minutes. It's like containing a nuclear explosion with a magnetic net, a fragile equilibrium, but one that could explain how these stars might persist long enough to leave observable traces. The simulations also reveal bizarre side effects. Some predict gravitational waves with unique frequency patterns, chirps too high-pitched for black hole mergers but too structured for supernova. Others suggest bursts of sterile neutrinos, hypothetical particles that could pierce through galaxies unimpeded. These signatures are now being hunted by observatories like LIGO and IceCube, turning theoretical quirks into potential detection blueprints. But the most tantalizing outcome, these models hint that electroweak stars might solve the mystery of certain ultra-long gamma-ray bursts. If a collapsing star's core rebounds as an electroweak engine, its neutrino jets could punch through the outer layers, creating shockwaves that produce gamma flashes lasting hours instead of seconds. It's a fringe idea, but when simulations and cosmic mysteries align, even fringe ideas demand attention. The universe, after all, has a habit of outdoing our wildest speculations. The question isn't whether we're ready to find an electroweak star, it's whether we'll recognize it when we do. Gravastars might be the most elegant cosmic loophole ever imagined, objects so bizarre they make black holes seem mundane. Picture this: instead of collapsing into a singularity, a dying star's core transforms into something straight out of quantum science fiction, a vacuum bubble encased in an ultra-thin, ultra-strong shell. At its heart, a void of dark energy, the same mysterious force accelerating the universe's expansion. Surrounding it, a crust so dense it defies conventional matter, a barrier so impenetrable even light can't escape its grip. This isn't just a black hole with extra steps, it's a radical rethinking of how gravity and quantum mechanics might dance at the edge of oblivion. The key difference lies in what happens at the center. Traditional black holes crush matter into an infinitely dense point where physics breaks down a singularity that even Einstein's equations can't describe. But gravastars offer an escape hatch. Their core isn't a singularity but a pocket of spacetime repurposed by dark energy, creating a stable, finite void. Think of it like a bubble in molten glass, hollow inside, yet surrounded by a shell so tough it mimics a black hole's event horizon from the outside. The shell itself is a marvel, a layer of exotic matter just a few Planck lengths thick, that's a millionth of a billionth of a billionth of a meter, yet strong enough to halt total collapse. Observationally, gravastars would be master impersonators. From a distance, they'd look nearly identical to black holes, warping light, bending orbits, and casting the same shadowy silhouettes. But subtle clues could betray their true nature. For one, their surfaces wouldn't evaporate via Hawking radiation like a black hole's event horizon. Instead, their rigid shells might vibrate when disturbed, ringing like cosmic bells and emitting gravitational waves with unique frequencies. Some models even suggest their shadows could flicker slightly, as light interacts with the shell's quantum structure in ways a true black hole couldn't replicate. The real magic, gravastars sidestep black holes' most infamous paradoxes. No singularity means no information loss dilemma. No event horizon means no firewall problem. The baffling idea that black holes might roast infalling matter with a wall of quantum energy. Even time behaves differently near a gravastar. While a black hole's gravity slows time to a stop at its horizon, a gravastar's shell could allow time to flow normally inside, creating a pocket universe cut off from our own. Critics argue gravastars require exotic matter with impossible properties, materials that defy known physics to maintain their structure. But supporters counter that the same quantum weirdness permitting black holes might also allow gravastars to exist. After all, if space-time can curve infinitely into a singularity, why couldn't it alternatively stabilize as a dark energy bubble? The answer might lie in merging quantum theory with relativity, a challenge that's already reshaping cosmology. For now, gravastars remain hypothetical, but that hasn't stopped astronomers from hunting for them. Some are scouring gravitational wave data for vibrations that don't match black hole mergers. Others are studying the flickering shadows at galaxy centers, searching for anomalies that might betray a shell's presence. If found, gravastars wouldn't just rewrite astrophysics, they'd prove the universe has more than one way to build a monster. And that's the beauty of cosmic mysteries. Sometimes the most outlandish ideas are just waiting for the right evidence to shine. Gravastars aren't just theoretical oddities, they're cosmic doppelgangers so convincing they could be fooling our most advanced detectors right now. When LIGO first detected gravitational waves in 2015, it confirmed black holes exist by catching the ripples from their collisions. But here's the unsettling truth. Those same signals might perfectly match what a gravastar collision would look like. The differences could be vanishingly subtle, buried in the fine print of spacetime's vibrations. At first glance, both objects behave similarly under stress. A black hole merger creates a distinctive chirp in gravitational waves, a rising frequency as the objects spiral inward, followed by a ring down as the new black hole settles into equilibrium. Gravastars, they'd produce nearly identical chirps during their inspiral phase, but the devil's in the ring down. Unlike a black hole's smooth decay, a gravastar's ultra-dense shell would wobble like a struck bell, adding faint overtones to the signal. The problem, current LIGO precision might not catch those extra vibrations unless they're unusually strong. It's like trying to distinguish two guitars by their echoes in a thunderstorm. The stakes couldn't be higher. If even one supposed black hole event was actually a gravastar, it'd force us to rewrite Einstein's predictions for how spacetime behaves under extreme conditions. Some theorists argue that certain detections already have anomalies, hints of extra frequencies in the ring-down that don't fit clean black hole models. Others counter that quantum noise or instrument artifacts could explain those glitches. Upcoming upgrades to LIGO and next-generation detectors like the Einstein telescope might settle the debate. With sensitivity sharp enough to hear a gravastar's quantum whispers, we could finally learn whether the universe prefers singularities or vacuum bubbles. Until then, every black hole shadow we photograph, every gravitational wave we detect, carries a thrilling uncertainty. The darkest objects in space might be hiding their true nature and the key to unlocking gravity's deepest secrets. Boson stars sound like something from the far future, a physicist's thought experiment brought to life, but they might be hiding in plain sight among the dark corners of our universe. Unlike the blazing furnaces of normal stars or the crushing densities of neutron stars, these objects are made of something far more ethereal, hypothetical particles called bosons, which don't follow the usual rules of matter. Picture a cloud the size of a solar system, held together not by gravity alone but by quantum mechanics on a cosmic scale, an invisible, ghostly structure pulsing with wave-like energy. If they exist, boson stars would be the universe's most delicate giants, massive yet diffuse, bending space-time without ever truly touching it. To understand why boson stars are so bizarre, we have to dive into the quantum realm. Ordinary matter, like the atoms in your body or the plasma in a star, is made of fermions, particles that obey the Pauli exclusion principle, meaning they can't occupy the same space at the same time. This is why neutron stars don't collapse further. Their fermions resist being squeezed together. But bosons, they're the ultimate team players. Particles like photons, which carry light, or the hypothetical actions a candidate for dark matter, can pile on top of one another without limit, forming a single, coherent quantum state. Under the right conditions, a colossal number of these bosons could clump together, creating a star-sized object that behaves less like a solid body and more like a ripple in space-time itself. The structure of a boson star would defy every cosmic norm. Instead of a crisp surface or a fiery core, it would resemble a fuzzy orb, densest at the center but gradually fading into the void. Some models suggest they could be as massive as dozens of suns, yet spread across a region larger than Neptune's orbit, meaning if you flew through one, you might not even notice. Their gravity would warp light, creating gravitational lensing effects, but without the crushing tidal forces of a black hole. They'd be nearly transparent, emitting no heat or light of their own, detectable only by the way they subtly bend the paths of distant stars or deflect passing radiation. The most tantalizing part, boson stars could solve two of astronomy's biggest puzzles at once. First, if they're made of actions, they might explain dark matter's elusive nature, acting as invisible anchors that sculpt galaxies without emitting a single photon. Second, they could be the true identity of certain ultralight black hole candidates, objects with the mass of a black hole but none of the destructive fury. Some astronomers have even proposed that the mysterious flares observed near the Milky Way center, often attributed to black hole activity, might instead be boson stars undergoing quantum ripples, their subtle vibrations releasing bursts of energy. Of course, proving their existence is a different challenge entirely. Boson stars don't just hide in the dark, they blur the line between particle and object, matter and energy. Current telescopes lack the precision to distinguish them from black holes or dense star clusters, but next-generation gravitational wave detectors might catch their unique frequency signatures. Unlike the violent collisions of black holes, merging boson stars would produce softer, wave-like disturbances in spacetime, like dropping two pebbles into a pond and watching the ripples intertwine. The universe has always been stranger than we imagine, and boson stars are a perfect reminder of that. They challenge us to rethink what a star even is, not just a ball of plasma, but a quantum phenomenon writ large across the cosmos. If we ever find one, it won't just be a new class of object, it'll be a window into the unseen fabric of reality itself, where the smallest particles and the largest structures are woven together by the same invisible rules. Finding boson stars would be like trying to hear a whisper in a hurricane, except the whisper isn't made of sound, but of space-time itself bending in ways we've never seen. Gravitational wave detectors like LIGO and Virgo have spent years listening for the violent crashes of black holes and neutron stars, but boson stars. Their collisions would sing a different tune entirely, a softer, more ethereal melody woven from the fabric of quantum fields rather than the thunderous roar of matter collapsing. Here's why their gravitational wave signature would stand out. When black holes merge, their event horizons slam together like cosmic cymbals, sending sharp, high-frequency ripples through space-time. But boson stars don't have surfaces or hard edges, they're more like giant quantum clouds. As two boson stars spiral toward each other, their wave-like particles would begin to overlap, creating interference patterns that ripple outward in smooth, oscillating waves. Instead of a chirp, detectors might pick up a humming vibrato, a sustained note with subtle harmonics that linger far longer than a black hole's abrupt ring down. The real breakthrough could come from future observatories like the Einstein telescope or space-based detectors like LISA. These next-gen instruments will have the sensitivity to catch lower-frequency gravitational waves, the perfect range for boson star mergers. Picture a collision between two of these quantum behemoths. Their dance could last for months, even years, as they gradually lose energy through gravitational radiation. Unlike black holes, which merge in a split second, boson stars would waltz in slow motion, their waves carrying fingerprints of their exotic composition. But the weirdness doesn't stop there. Because boson stars are governed by quantum mechanics, their mergers might produce bursts of scalar radiation, a type of gravitational wave unique to theories beyond Einstein's relativity. This would be the smoking gun, a signal no black hole or neutron star could replicate. Some models even suggest these events could emit gravity lasers, coherent beams of gravitational waves that would streak across the universe like cosmic searchlights. Of course, the challenge is separating these signals from the noise of the universe. Gravitational wave detectors are already drowning in false alarms, glitches from seismic tremors, equipment hiccups, even passing trucks. Identifying a boson star's whisper will require AI sifters trained to spot quantum subtleties in the data, algorithms fine-tuned to listen for the universe's quietest secrets. Yet the payoff would rewrite physics. Detecting a boson star wouldn't just confirm their existence, it'd prove that dark matter can clump into star-sized objects, that quantum effects can scale to cosmic proportions, and that gravity's symphony includes notes we've never dreamed of. The universe has always been stranger than we imagined, and somewhere out there, hidden in the static of space-time, boson stars might be waiting to sing. Among the universe's strangest hypothetical objects, cue balls stand out as cosmic anomalies that blur the line between particle physics and astrophysics. Imagine a bubble of pure, concentrated energy, not a star, not a black hole, but a stable, star-sized knot of scalar fields, theoretical entities that permeate the fabric of space-time. These wouldn't simply float in space, they'd warp it, their sheer density bending light and distorting orbits without emitting so much as a flicker of radiation. Cue balls sound like science fiction, yet they emerge from legitimate extensions of quantum field theory, offering a wild explanation for dark matter and even relics from the universe's first moments. The physics behind cue balls is as elegant as it is bizarre. In certain theories, scalar fields, think of them as invisible, universe-filling energies, can clump together into stable configurations like soap bubbles in a quantum foam. Unlike ordinary matter, these clumps don't rely on gravity or nuclear forces to hold themselves together. Instead, they're bound by the inherent properties of the scalar fields, forming what physicists call non-topological solitons. Picture a drop of water suspended in zero gravity, its surface tension keeping it perfectly spherical. A cue ball is like that, but instead of water, it's made of raw field energy, and instead of surface tension, it's held together by the field's self-interactions. What makes cue balls truly mind-bending is their potential scale. While theories initially imagined them as microscopic, some models allow for stellar or even galactic sizes. A star-sized cue ball could weigh as much as the Sun, yet be completely invisible, its energy locked in a form that doesn't interact with light. If such objects exist, they'd be floating through galaxies right now, their gravitational pull the only hint of their presence, making them perfect dark matter candidates. No need for exotic particles. Dark matter could simply be an ocean of these invisible, energy-packed blobs. Cosmologically, cue balls could be fossils from the universe's infancy. During cosmic inflation, the rapid expansion thought to have shaped the early cosmos scalar fields might have fractured into dense regions that later collapsed into cue balls. These relics would have survived nearly untouched for billions of years, frozen in time like flies in amber. If we found one, it'd be a time capsule from the first trillionth of a second after the Big Bang, holding clues about forces and energies we've never observed directly. The hunt for cue balls is already underway, albeit indirectly. Some experiments search for their explosive decay signatures, hypothetical bursts of high-energy particles that would betray their presence. Others look for gravitational lensing anomalies where no visible object exists. But the most tantalizing possibility, they might already be hiding in data from cosmic ray observatories or neutrino detectors, their subtle fingerprints overlooked because no one knew what to look for. Discovering a cue ball would rewrite more than just astronomy textbooks. It'd prove that the universe can stabilize pure energy into macroscopic objects, that dark matter might not be particles at all, and that scalar fields, long relegated to theory, can shape reality on cosmic scales. Whether they're lurking in deep space or waiting to be created in a lab, cue balls remind us that the universe's rulebook still has blank pages, and sometimes the most outlandish ideas are the ones holding the pen. If cue balls drift unseen through galaxies, their ghostly presence could solve one of astronomy's most persistent puzzles: why galaxies spin faster than they should. Take our Milky Way. Stars orbiting the outer edges move at velocities that defy Newton's laws, as if gripped by an invisible hand. Scientists call this discrepancy dark matter's fingerprint, but the nature of that matter has remained elusive. Cue balls offer a radical solution. Unlike hypothetical particles like WIMP, which require complex detectors to spot, these macroscopic blobs of scalar field energy could weave through galaxies like cosmic icebergs, their immense mass tugging on stars without ever colliding with them. Picture a spiral galaxy's rotation curve, the graph plotting stellar speeds against their distance from the center. Normally, you'd expect outer stars to slow down like planets farther from the Sun. Instead, curves flatten, with stars whipping around at near constant speeds no matter their orbit. Traditional dark matter models explain this with halos of diffuse particles, but cue balls propose something more audacious: a scattered population of dense, invisible objects, each weighing anywhere from an asteroid to a star. Their gravity would collectively warp space-time like stones in a stretched sheet, creating the precise rotational anomalies we observe. The elegance lies in their simplicity. While particle-based dark matter requires delicate fine-tuning to match observations, cue balls naturally produce flat rotation curves just by existing. Their size and distribution could vary. Some might cluster near galactic cores, while others drift in the outskirts, but their cumulative gravitational effect would be indistinguishable from the smooth halos we've long assumed. Even stranger, cue balls could explain why some galaxies seem to have too much dark matter. If a galaxy formed in a region dense with these objects, its rotation would appear anomalously fast, matching oddballs like Dragonfly 44, a galaxy 99% dark matter by mass. Yet the real test of this theory isn't just math, it's observation. Cue balls, unlike traditional dark matter, might leave subtle scars on their surroundings. As they pass through gas clouds, their gravity could compress interstellar material, triggering star formation in unexpected patterns. Some astrophysicists speculate that certain dark galaxies, regions rich in hydrogen but devoid of stars, might actually be cue ball nurseries, their gas squeezed into filaments by the object's passage. Others suggest that if cue balls occasionally decay, they'd release bursts of high-energy radiation, creating unexplained gamma-ray hotspots in otherwise quiet regions of space. The hunt for these signatures is already underway. Teams are scouring radio telescope data for anomalous star-forming regions and cross-referencing gamma-ray maps with gravitational lensing surveys. Even a single confirmed cue ball would upend decades of dark matter research, proving the universe prefers energy knots over particles. It's a long shot, but as history shows, the cosmos rarely plays by the rules we expect. Whether cue balls are real or not, their mere possibility forces us to ask, what if dark matter isn't a particle at all, but a shadow universe of quantum structures we've only begun to imagine? Among the most elusive predictions in physics are magnetic monopoles, single-poled magnets that defy everything we know about magnetism. Imagine a particle that isn't just a tiny bar magnet with north and south stuck together, but a solitary north or south pole wandering freely through space. Theorized by grand unified theories, these exotic particles could clump together under gravity, forming something even stranger: magnetic monopole stars, celestial objects where the usual rules of electromagnetism twist into something unrecognizable. At their core, these stars wouldn't just defy magnetism, they'd rewrite it. In a normal star, magnetic fields loop from pole to pole, shaping solar flares and stellar winds. But a monopole star's field lines wouldn't connect. They'd radiate outward like spokes from a wheel, creating a magnetic force so intense it could strip electrons from atoms light years away. Picture the star's surface crackling with currents we can't see, its entire structure held together not just by gravity but by the sheer pressure of its own monstrous magnetic field. The formation of such a star would require conditions almost too extreme to fathom. In the early universe, phase transitions, moments when fundamental forces split apart, might have forged monopoles in vast numbers. If enough clustered together, their collective gravity could collapse them into a star, their magnetic charges aligning into a coherent macroscopic force. Unlike ordinary matter, monopoles wouldn't need fusion to generate energy. Their interactions alone could heat the star to millions of degrees, powering it through magnetic annihilation, a process where north and south monopoles collide and release bursts of pure energy. The strangest part, these stars might not even look like stars. Without the turbulent plasma of a sun, their surfaces could resemble a vast, smooth magnet, emitting no light but warping space-time with their gravity and twisting nearby particles into spirals. Their magnetic fields would be so powerful they'd bend cosmic rays into jets, creating invisible particle accelerators in deep space. Some models suggest they could even mimic pulsars, but instead of radio waves, they'd emit pure magnetic distortion, a hum detectable only by its gravitational side effects. Yet the most tantalizing possibility is that monopole stars could still exist today, hiding in the voids between galaxies. Their lack of light makes them nearly undetectable, but their gravity and magnetism would leave subtle scars, unexplained cosmic ray hotspots, or galaxies with bizarrely twisted magnetic fields. If we ever found one, it wouldn't just confirm a cornerstone of grand unified theories, it'd prove the universe can build stars from the raw ingredients of force itself. The hunt is on, not for light, but for the invisible fingerprints of magnetism's most elusive children. To understand how monopole stars could form, we have to rewind the cosmic clock to the universe's earliest moments when the fundamental forces we know today were still fused into a single, unified power. In the searing heat of the first trillionth of a second after the Big Bang, the cosmos wasn't just expanding, it was undergoing radical transformations, like metal cooling from molten to solid. These phase transitions weren't just temperature shifts, they were moments when the very fabric of reality reconfigured itself, and one of the most dramatic shifts involved the birth of magnetism as we know it. Picture the universe as a bubbling cauldron of energy, so hot and dense that electromagnetism and the nuclear forces were indistinguishable. As the cosmos expanded and cooled, symmetry broke like ice crystals forming in water, and the forces split apart. But just as freezing water can trap air bubbles, these cosmic cracks might have left behind defects, knots of magnetic energy that didn't smooth out evenly. These defects would have become magnetic monopoles, solitary north or south poles adrift in the newborn universe. Now, here's where things get wild. If monopoles were produced in vast numbers during this epoch, as some grand unified theories predict, their sheer density could have led to gravitational clumping on scales we barely comprehend. Unlike ordinary matter, which spread out as the universe expanded, monopoles could have clustered into dense regions, their mutual attraction weaving them into colossal structures. Over billions of years, these knots might have collapsed under their own gravity, forming stars where magnetism, not fusion, dictated the rules of existence. What's fascinating is how these objects would defy the universe's usual balance. In normal stars, magnetic fields are secondary players, shaping solar flares but bowing to gravity's dominance. But in a monopole star, magnetism would be the star's backbone, its field lines radiating outward like a cosmic spiderweb. The energy release from monopole annihilation, north and south poles crashing together, could sustain the star's heat without a single nuclear reaction, creating a celestial object glowing with invisible fury. The echoes of this process might still linger today. If monopole stars formed in the early universe, some could have survived, drifting through the voids between galaxies like dark, magnetized titans. Others might have seeded the supermassive black holes we now see at galactic centers, their immense magnetic fields accelerating the collapse of surrounding matter. And if even a handful persist, their influence could explain some of astronomy's lingering mysteries, like the unexplained cosmic rays with energies far beyond what particle accelerators can produce. The hunt for these relics is more than a quest for exotic stars. It's a window into the universe's first moments when the rules of physics were still being written. Every unexplained magnetic anomaly in deep space, every bizarre particle shower from seemingly empty voids, could be a clue that the cosmos once built stars from the raw ingredients of broken symmetry. The universe, it seems, has a flair for the dramatic, and monopole stars might be its most audacious performance yet. Strange-lit stars are perhaps the most unnerving hypothetical objects in the cosmos, not just because of what they are, but because of what they could do. Picture a star that doesn't merely burn or collapse, but one that rewrites the very composition of reality on contact. These theoretical monsters would be composed of strange quark matter, an exotic state where up and down quarks, the building blocks of protons and neutrons, are joined by a third flavor, strange quarks. Under extreme pressures, this trio could form a stable, ultra-dense material unlike anything in our everyday experience. The terrifying twist: if strange matter is truly the most stable form of matter in the universe, as some theories suggest, a single encounter between a strange-lit star and ordinary matter could trigger a runaway conversion, transforming everything it touches into more strange matter. A stellar handshake that could rewrite entire galaxies. The process would be chillingly elegant. Strange quark matter is theorized to have a lower energy state than normal atomic matter, meaning it's inherently more stable. If a chunk of this material, say, a fragment from a strange-lit star's surface, drifted into a planet or a normal star, the contact could catalyze a chain reaction. Protons and neutrons in the victim's atoms would unravel, their quarks reassembling into strange matter, releasing energy in the process. That energy would then fuel further conversions, spreading like a cosmic virus. The result, an object that started as a harmless asteroid or gas cloud could, in theory, collapse into a pulsating knot of strange matter, its gravity and composition forever altered. It's the ultimate cosmic contagion, a silent apocalypse playing out at the subatomic level. This nightmare scenario has earned strange-lit stars a notorious place in debates over cosmic censorship, the idea that the universe naturally prevents certain catastrophic phenomena from being observable. Some physicists argue that if strange matter were this dangerous, we'd already see evidence of its destructive potential. After all, the universe is ancient and cosmic collisions are frequent. The fact that we still exist, they say, suggests strange-lit stars either don't form or are extraordinarily rare. Others counter that cosmic censorship might not be a universal law, but a fluke of our local environment. Strange-lit stars could lurk in distant galactic voids, their conversion waves smothered by the vast emptiness between stars. Or perhaps they're shielded by magnetic fields or quantum effects we don't yet understand, their apocalyptic potential contained by physics we've yet to uncover. The stakes of this debate are staggering. If strange-lit stars exist, they'd challenge our understanding of matter's fundamental stability. They'd force us to confront the possibility that certain regions of the universe are fundamentally uninhabitable, not because of radiation or gravity, but because their very chemistry is hostile to life as we know it. Even more unsettling, some models suggest that neutron stars, already dense, already bizarre, could spontaneously transition into strange-lit stars under the right conditions. A flicker of quantum instability and a pulsar we've studied for decades could, in theory, transform into something far more sinister, its new nature hidden until it's too late. Yet for all their apocalyptic potential, strange-lit stars also offer a tantalizing clue about the universe's origins. If they're real, they could be relics of the quark-gluon plasma that filled the cosmos microseconds after the Big Bang, frozen into stellar form. Studying them, even theoretically, might reveal secrets about how matter transitions between phases, how symmetry breaks, and how the building blocks of reality itself assemble under pressure. The irony is delicious. The same objects that could erase worlds might also hold the key to understanding creation. So far, we've found no definitive evidence of strange-lit stars, but the search is far from over. High-energy particle colliders like the Large Hadron Collider have briefly recreated quark-gluon plasma, hunting for signs of strange matter's stability. Astronomers scour neutron star collisions for anomalies in gravitational wave signatures that might betray a strange transformation. Even cosmic ray detectors keep watch for ultra-dense particles that could be strange-lit fragments ejected from some distant cataclysm. Every null result is a small relief, but also a reminder that the universe specializes in surprises. Whether they're lurking in the dark or confined to theory, strange-lit stars stand as a humbling testament to just how little we truly know about the rules of existence. And that, perhaps, is the most unsettling thought of all. The notion of strange-lit stars unleashing a doomsday scenario across the cosmos is the kind of idea that fuels both scientific debate and late-night existential dread. Picture this: a fragment of strange quark matter smaller than a grain of sand drifts into Earth's atmosphere. On contact, it begins converting ordinary atoms into more strange matter, triggering an unstoppable chain reaction. Within hours, our planet could shrink into a dense, city-sized orb of exotic material, its continents, oceans, and every living thing rewritten at the subatomic level. It's a cosmic horror story ripped straight from science fiction, but could it actually happen? Physicists have grappled with this possibility for decades, and while the math doesn't outright dismiss it, the consensus leans heavily toward skepticism. Here's why. For a strange-lit apocalypse to unfold, several fragile assumptions must align perfectly. First, strange quark matter would need to be absolutely stable, a property that, while theoretically possible, has never been observed. Experiments at facilities like the Large Hadron Collider have recreated quark-gluon plasma, the primordial soup where strange matter could form, but no signs of stable strange-lits have emerged. If they're not appearing in conditions that mimic the early universe's extreme energy, their natural existence becomes far less likely. Second, even if strangelets can form, they'd need a delivery mechanism. Cosmic rays bombard Earth constantly, yet we've never detected particles with the telltale density of strange matter. Neutron-star collisions, often cited as potential strangelet factories, tend to eject material too violently for coherent chunks to survive. The distances between stars are also a saving grace. Any strangelets wandering the galaxy would take millennia to reach us, and the odds of a direct hit are astronomically slim. But the most compelling counterargument lies in the universe's own resilience. If strange matter were this virulent, the cosmos would have already shown signs of infection. Older regions of space, where stellar collisions are more frequent, should be riddled with strangelet-converted remnants, yet telescopes see no evidence of planets or stars abruptly vanishing into ultra-dense knots. The Milky Way's longevity suggests that if strangelets exist, they're either extraordinarily rare or bound by stabilizing forces we don't yet understand. That said, science thrives on ruling out the improbable. Researchers continue to monitor heavy ion collisions and neutron star mergers for anomalies, and projects like the Alpha Magnetic Spectrometer on the International Space Station scan cosmic rays for strangelet signatures. The search isn't just about averting hypothetical doom, it's a window into quark behavior under conditions we can't replicate on Earth. So while the idea of a strangelet star rewriting the cosmos makes for gripping storytelling, the universe seems to have built-in safeguards. Whether through quantum stability, cosmic distribution, or sheer luck, the night sky remains reassuringly free of self-replicating matter-eaters. For now, at least, we can keep gazing upward without fearing the dark. Mirror matter stars don't just defy expectations, they rewrite the cosmic rulebook entirely. Picture a celestial object built from particles that are perfect reflections of our own, identical in every way except one. They interact with our universe only through gravity. These wouldn't be stars as we know them, no blazing light, no solar flares, just silent, shadowy spheres drifting through space, invisible to every telescope, detectable only by the way their gravity tugs on the visible cosmos around them. The concept comes from a radical idea in physics that our universe might have a hidden twin, a parallel realm where matter is structured like ours but flipped, as if seen in a quantum mirror. If mirror matter exists, its stars would be the ultimate cosmic ghosts. Their protons, electrons, and neutrons would have mirror counterparts, obeying the same physical laws but completely oblivious to our photons, our electromagnetic fields, even our air. You could pass your hand through a mirror star like a ghost walking through a wall, feeling nothing, seeing nothing, yet its gravitational pull might be strong enough to bend the path of a comet or distort the orbit of a planet. Some theories suggest these stars could explain the Milky Way's missing mass problem, those stubborn gravitational anomalies that hint at invisible matter we've never been able to pin down. The strangest part, mirror stars might not just be passive observers in our universe. If they collide with ordinary matter, say plowing through a nebula, their gravity could compress the gas around them, triggering star formation in eerie, unexplained patterns. Galaxies could harbor entire clusters of mirror stars, their presence betrayed only by the way they sculpt the orbits of visible stars or warp the light of distant quasars. Astronomers have even speculated that certain gravitational microlensing events, brief brightenings of distant stars with no apparent cause, might be mirror stars passing silently in front of them, their unseen mass bending space-time just enough to magnify the light behind them. Yet the most tantalizing possibility is far more unsettling. If a mirror star's core collapsed, it wouldn't form a black hole as we understand it. Instead, it might create a mirror black hole, a singularity that emits no Hawking radiation we could detect, no X-rays, no gamma-ray bursts. It would be a perfect cosmic trapdoor, swallowing matter from its own universe while leaving ours untouched. the implications are staggering. Entire galaxies could be threaded with these invisible vortexes, their presence measurable only by the way they twist the fabric of spacetime itself. The hunt for mirror matter isn't just academic. Experiments like the Neutron EDM project are searching for subtle asymmetries in neutron behavior that could hint at interactions with a hidden mirror universe. Others analyze cosmic ray data for particles that seem to vanish, as if briefly slipping into a parallel realm. If mirror stars exist, they'd be the ultimate test of how deeply the universe's secrets are hidden not in distant galaxies or exotic particles, but in the ghostly echoes of a reality just beyond our grasp. The cosmos, it seems, has a knack for keeping its most profound mysteries one reflection away. While mirror stars remain invisible to conventional telescopes, they might leave fingerprints in the most elusive particles known to science, neutrinos. These ghostly subatomic particles, capable of passing through entire planets without a trace, could be our only direct window into the hidden universe of mirror matter. Picture this: a mirror star undergoes a cataclysmic event in its shadowy realm, releasing a burst of mirror neutrinos. Normally, these would zip through our world undetected, but according to some theories, there's a slim chance they could oscillate into ordinary neutrinos we can observe. It's like catching a whisper from another dimension, a fleeting signal that betrays the presence of something vast and unseen. Detecting such a signal would require untangling cosmic needles from haystacks. Neutrino observatories like IceCube in Antarctica or Super Kamiok and in Japan are already tuned to catch high-energy neutrinos from supernova and black holes. But mirror star neutrinos would carry telltale anomalies, unexplained energy spikes with no visible source, arriving from regions of space that appear empty. Some researchers speculate these could manifest as double pulses, split-second flashes where a single neutrino event seems to flicker twice, as if the particle briefly straddled both realities before settling into our own. The challenge lies in distinguishing mirror neutrinos from the constant background noise of cosmic rays and solar neutrinos. Advanced AI is now scouring decades of data for statistical oddities, patterns that defy known astrophysical processes. One tantalizing candidate emerged in 2017 when IceCube detected a neutrino with energy levels suggesting an extragalactic origin, yet no matching gamma-ray burst or supernova was found. Could this have been a mirror star's distant echo? The implications stretch beyond mere detection. If mirror neutrinos can cross between universes, they might carry information about the fundamental symmetries of physics. Are the forces in their universe identical to ours or slightly skewed? Do their stars burn hotter, age slower, or follow different quantum rules? Each anomalous neutrino could be a cipher holding answers to questions we haven't even thought to ask. What makes this hunt so electrifying is its duality. It's not just about finding invisible stars, but probing the boundaries of reality itself. Every unexplained neutrino signature is a potential clue that the cosmos is far richer than our eyes can see. And if we ever confirm a mirror star's signal, it won't just expand our map of the universe, it'll tear a hole in the very fabric of what we thought was possible. Deep within the twisted depths of string theory lies a possibility so strange it challenges our notions of reality itself. Planck core remnants, the hypothetical corpses of collapsed universe brains. To understand these cosmic oddities, we need to venture beyond ordinary black holes and quantum foam into realms where spacetime itself unravels at the smallest possible scale. Imagine a dying universe, not our own, but a neighboring brain in the multiverse crunching inward until every ounce of its existence compresses into a single, unfathomably dense point no larger than the Planck length. That's a trillionth of a trillionth the size of a proton. What remains isn't a singularity in the traditional sense, but a fossilized knot of higher dimensional spacetime, vibrating with the echoes of a dead cosmos. String theory paints these remnants as anything but inert. At Planck scales, the usual rules of general relativity and quantum mechanics collide violently, and it's here that the remnants might reveal their true nature. Their cores could be threaded with cosmic strings, one-dimensional defects in space-time, or shimmer with brain dust, fragments of disintegrated higher-dimensional membranes. Some models suggest they might even harbor trapped pockets of alternate physics, where forces we've never witnessed briefly flicker into existence before dissolving back into the quantum static. The real mind-bender, these remnants might not stay hidden. If one drifted into our universe, its Planck-scale size wouldn't diminish its gravitational might. A single core could weigh as much as a mountain, warping space-time around it like a pinprick black hole. Yet, unlike black holes, Planck cores wouldn't evaporate via Hawking radiation. Their structure could be immune to decay, making them practically immortal. You could fly a spacecraft within millimeters of one and never know it was there until your trajectory bent inexplicably, as if space itself had developed a tiny, invisible warp. Detecting these phantoms would require rethinking physics itself. Traditional telescopes are useless against objects smaller than atoms, but gravitational wave detectors might catch the ripples from a Planck core's passage. More radical proposals suggest using quantum entanglement, purposefully entangling particles and monitoring for disturbances that might betray a remnant's presence as it brushes past. It's a cosmic game of hide and seek where the hider doesn't even obey the same dimensional rules. The implications stretch far beyond curiosity. If Planck cores exist, they could be the ultimate time capsules, preserving data from dead universes in their vibrational patterns. Some theorists speculate they might even seed new Big Bangs, their pent-up energy birthing fresh cosmos like quantum phoenixes. Others warn they could destabilize our universe's vacuum state, a single decaying core potentially triggering a catastrophic phase transition that rewrites the laws of physics in its wake. For now, Planck core remnants remain ghosts in the equations, their existence hanging on the unproven tenets of string theory and brane cosmology. Yet the mere possibility reminds us that the universe's deepest secrets might not lurk in the vastness of space, but in the infinitesimal cracks between dimensions, where fragments of dead realities wait, silent and patient, for someone to decipher their echoes. From primordial dark stars fueled by annihilation of dark matter to mirror matter stars lurking in parallel universes, we've explored 25 of the most bizarre, elusive objects the cosmos might harbor. Each one pushes our understanding of physics to the breaking point: stars that don't shine, monsters made of quark soup, gravitational ghosts detectable only by the ripples they leave in spacetime. Imagine the revolution if just one of these were confirmed. Electroweak stars proving forces can unify at stellar scales, boson stars revealing dark matter's true face, or frozen stars bending time itself into cosmic illusions. The implications would ripple through every textbook, forcing us to rewrite how galaxies form, how matter behaves under extreme conditions, even how the universe began. Yet the real magic lies in the hunt itself. Every anomaly in telescope data, every unexplained gravitational wiggle could be the first clue. The James Webb Space Telescope might spot a primordial dark star's infrared whisper. Gravitational wave observatories could catch the hum of colliding quark stars. Neutrino detectors may intercept signals from mirror matter collisions in realms we can't see. This isn't just astronomy, it's detective work on a cosmic scale where every observation could crack open a new chapter in reality's rulebook. So tell us which of these dark stars captures your imagination: the time-bending frozen stars, the apocalyptic strangelet converters, or perhaps the Planck core remnants carrying echoes of dead universes. Drop your thoughts below, and if you're hungry for more mysteries lurking beyond the visible cosmos, hit subscribe. The universe is stranger than we've dared to dream, and together we'll keep unraveling its secrets one dark star at a time.